Welcome to this unit on the coupling of the DEM with CFD as well as multiphysics applications. As you might know, CFD stands for computational fluid dynamics, which means that continuum models for fluid flow are numerically solved using a software tool. As always, we will start with an overview of what you will learn. Specifically, we will start with applications in which the coupling of the DEM with CFD and the finite element method, or short FEM, is essential. We will then have a short chapter that allows you to pick the right strategy for such a coupling, including a guideline for judging feasibility. A chapter on some CFD essentials, which we call CFD in a nutshell, is also included. The final chapter of this unit is dedicated on how to couple, meaning we will provide the necessary background to understand coupling algorithms as well as the most important software implementation strategies. Before we go on and go into medias res, let me give you a very coarse overview of how coupling is achieved. As CFD-DEM is a huge topic, I was forced to spare out some details. This includes an introduction to CFD, turbulence details, and the basics of numerics. You will find books as well as other training materials certainly somewhere else, for example in your favorite MOOC on CFD. Before we go into medias res, let me give you a very coarse overview of how CFD coupling is achieved in principle. As you can see in this figure, CFD and DEM are typically encapsulated in different software tools and have their own time loop. The CFD loop is typically the outer loop that has a larger time step. After mesh initialization, particle data is drawn to calculate all necessary continuum quantities, e.g. the particle volume fraction. Subsequently, the governing equations in the Navier-Stokes equations are solved, and information, essentially the pressure and velocity field, are handed over to the DEM solver. In the right panel, the DEM time loop is illustrated, which runs typically 10 times during a single CFD time step. With this fundamental understanding, we can now progress to our applications chapter. The application of a computational model is always driven by the question, why should we use this model and not another one? For CFD-DEM, the first potential answer to this question is that fluid coupling is a door opener to many applications that neither classical CFD nor DEM alone can attack. Such applications often include small particles, meaning that the key dimensionless number in a fluid particle flow, which is the Stokes number, is below a critical limit. We will see later that the Stokes number also should not be too small, otherwise particles would perfectly follow the fluid and there is simply no need for a two-phase simulation. The second criterion is that a strong coupling between the two phases exists. This means that the local mass loading of the dispersed phase, i.e. the particles, is significant. Typically, we are talking about a local mass loading mu of larger than 0.1 kg particles per kilogram fluid. Note that the local mass loading in a flow situation may be significantly larger than the global one. Particles are not always homogeneously distributed. How such a flow looks like and what causes the difference between local and global mass loading is illustrated here on the bottom left. Specifically, we see a freely sedimenting gas particle suspension at different Froude numbers that spontaneously and dynamically form clusters, i.e. regions in which particles have a higher concentration. As you can see, the Froude number has an effect on the size of the clusters, and hence how significantly the differences between the local and global mass loading are. Examples for applications in which the mass loading is high and the Stokes number is in an interesting range and consequently CFD-DEM coupling is used include fluidized bed simulations. Such simulations can be performed on a fundamental level, as the setup shown here on the left, or also up to pilot scale applications which are in reach when using CFD-DEM simulations. Another topic in which CFD-DEM simulations are interesting include cyclone separators, especially highly loaded cyclones used in circulating fluidized bed applications can be simulating using CFD-DEM. Next, coupled simulations are also relevant for the fundamentals of filtration processes, e.g. to better understand how a certain filtration device works. Also, we should not forget about powder transport systems that often rely on dense or dilute phase conveyors that use air as the transport medium. Last, sediment transport in rivers and other geophysical applications are attractive for coupled CFD-DEM simulations, as both the Stokes number and the mass loadings are in an interesting range. But this is not the only motivation. The next one originates from the fact that the combination of different physical phenomena, often called multiphysics effects, are relevant for a certain industrial implication. Consequently, simulating this combination of phenomena can be of large value for an industrial sector. An example is the field of polymer processing, for which you see a simulation on the bottom left. What you see here is the temperature and the phase distribution of the particles in the melt in the top panel, as well as the isosurface of the molten phase at the bottom. Such simulations are valuable to optimize the geometry of the extruder, which would be very expensive by using experiments. The next set of applications in which multiphysics effects are important is motivated by the fact that often precise analytical or continuum models are simply not available. As you see here on the left, this is the case for certain high temperature applications in which, next to classical heat conduction and convection, also radiative energy transport is important. Also typical for such applications is that there is a distribution of particle temperatures, here on the left, as well as of particle masses, here shown on the right. Capturing this distribution is critical for accurate predictions of process performance. For example, how quickly this bed of particles can be combusted. Other examples that fall into this category include fluidized bed granulators, which are relevant for food and pharma applications, blast furnaces to produce steel, and the already mentioned combustion application, e.g. of biomass, and also gasification and pyrolysis of biomass feedstock. Let us now consider the coupling of the DEM with structure mechanics, i.e. so-called FPSI applications, which is the short form of fluid particle structure interaction. Often it's only called FSI, but we don't use that wording here on this slide. In such applications, also no analytical approach is useful since there is a high nonlinearity in the model itself, or the nonlinearity develops due to the coupling. Let's have a look at this video here on the left that shows such an application, namely the prediction of wear due to particles hitting a chute. As you can imagine, when replacing the chute with other materials, e.g. a piece of soil, a whole range of interesting wear prediction problems can be studied. Another fascinating application of FPSI is motivated by the simple fact that no continuum model can be built to replicate some applications. Specifically, look at this example in which an already complex gas-liquid flow with a free interface, i.e. waves, is interacting with flexible fiber-like particles. Clearly, as you can see, if you look closely, a continuum model for these particles does not exist, and even if it would be extremely difficult to couple it to this two-phase flow. With this impressive simulation from DCS computing, I would like to go on and continue with the next chapter, which focuses on strategies to realize CFD-DEM coupling, as well as ideas on how to judge the feasibility of a certain CFD-DEM simulation.